You may recall our definition of potential energy when you do work to store energy due to position. And we talked about it for gravitational force. We can also think about it for the spring force. So here I have a mass on a spring, and right now the mass has no kinetic energy, and we can define this position as having no potential energy. So if I do some work on the system, now I've given it potential energy, and if I release it, it's free to convert that to kinetic. And in this system, it goes back and forth from kinetic to potential. So let's look at and calculate the spring's potential energy. So I'm going to draw it and think about it sideways. That way we don't have to do spring and gravity at the same time, because nobody wants to do that. So say this, you could think of this if you want as the natural length of the spring, this position, and we are going to push it to here. All right, so we have a finger here, and we pushed it, FP. And bunched up the spring, coiled it up really tight, because we're getting higher state of potential energy. And we're going to draw an axis, say like this. And we're going to go along the x-axis, plus x direction, and we'll call the initial position A and the second position B. So we push the thing from A to B. So let's see, the work to move the mass from A to B is what we need to calculate, because we always do a work calculation to figure out potential energy. So let's see, that would be the work equals the integral of F dot dx in this case. Right. So there are simple versions of work. Work is F times d. And then if you want to really do vectors, it's F dot displacement. But if the force varies with position, as it does with Hooke's law for a spring, you have to do an integral if the force varies. So this is a case, of course, where the force varies. And we're going to integrate from what I'll call XA to XB. Okay? So let's see, we would plug in and say the work then is equal to the integral from XA to XB. And we got to think, now it's a dot product between the force and dx. And actually the force we're applying is forward. We're not really calculating the spring's force, we're calculating the external force. It's an external work. So we're pushing externally with a force kx, right? I'm going to leave that negative sign out from Hooke's law because I'm not calculating the spring's force, I'm calculating our external force. So that's kx and then dx, and the dot product isn't there because they're the same direction. So the angle between the force and the displacement is 0, so cosine of 0 is 1. So got rid of not showing the vector part at this point. All right, so this integral of kx becomes 1/2 kx squared. 1/2 kx squared evaluated from xa to xb. Right, and then we could say that the work then is 1/2 kxa squared minus 1/2 kxb squared. Right? Okay, so now we got to think about it to do our sort of mental version of what potential energy means, is once we move it to B, at B, it has the potential to gain kinetic energy, is one way to think about it. All right. How much could it gain? Well, if we define u equals 0 at x equals xa, then that makes this part 0. Therefore, I'm sorry, let's see. Yeah, sorry. This wasn't coming out right. xb minus xa, there we go. So if we define u 0 at x equals xa, basically say that term is 0, then the potential energy is 1/2 kxb squared, or just 1/2 kx squared. The potential due to a spring is 1/2 kx squared. If you define the potential to be 0, where x is 0. If you want the potential difference between two positions, this would be the potential energy. 1/2 kx squared final minus 1/2 kx squared initial. So now we have a second potential to think about when we do conservation of energy problems. Now we're going to talk about the mechanical energy of the crossbow. Now I always carry a personal crossbow like this. This is a little 3D printed crossbow that I use to protect my family. I found it on Thingiverse. It's pretty nice by user Sens, and it's one piece, and you just add the string, and there you go. I like to fire matches with this crossbow. So let's see, put a match in here and say, oh, leave me alone. We shoot it like that. Okay, so what we're going to do is estimate how high the match should go, because we have two kinds of potential energy. We have gravity, if we shoot it straight up, and we also have the springiness of the bow. So first let's calculate and see what we expect to get with some reasonably realistic numbers here. So first of all, it's an energy problem. We're going to do it by conservation of mechanical energy. We're going to say that the change in mechanical energy equals 0. So we can break that up into the individual terms we care about. The change in kinetic plus the change in gravitational potential plus the change in spring energy potential equals 0. And if we think about it, what we're going to do is have, let's see, we're going to define 0. The origin is where the mass or the match first sits. We'll approximate the match as a point particle. Of course, that makes sense. And the spring, we'll say the spring's natural length would be up to here, right? So when we compress the spring is going to push up a distance we'll call d. So as we go up in the y direction, like that, it pushes up to d. But then the question is, how high are we going to get? How high is the thing going to go once it's released by the spring and goes up? We'll call that height. We'll just call that the y position. Okay, so we have all that. So then we need to say delta k, the change in kinetic energy. It's actually 0. We're starting with 0 kinetic energy. We're accelerating up, and then we're slowing down due to gravity and coming to a stop right at the top. Okay, so the final kinetic energy is 0 minus the initial kinetic energy is 0. So that one was easy. The change in gravitational potential energy. So the final is mgy, that's how high it got, minus the initial is mg0. That's why we made that the origin. Right? So the change in gravitational potential is just mgy, where y is how high it got. And then the spring potential energy, let's see, so that would be final minus initial. So the final spring energy is 0 minus, and then the initial is 1/2 k and the deflection of the spring squared. So 1/2 k, and then we did the spring by d squared equals 0. So you should be able to use that information to get y, right? So now we can start throwing in some realistic numbers. The mass of a match, it's roughly 0.2 of a gram, right? So that's in kilograms, 0.0002 kilograms. Gravity, 9.8. Y is what we're looking for. We can bring this to the other side and say equals 1/2 k of the spring. So I kind of measured it. It's kind of a nonlinear spring, so it's a little tricky, but it's about 10 newtons per meter. Plastic springs like that don't follow Hooke's law that well. That's a pretty good estimate. 10 newtons per meter. And then the d that you deflect it by is 2 centimeters, so 0.02 meters squared. Solve this around for y, and coincidentally, y is about a meter. Y 1 meter, approximately. These are all very approximate numbers for you here. All right, so let's see if that's really what happens. So what I'm going to do is sort of stick it in this clamp just to hold it still and hold it at a pretty good height. It's sitting here about 50 centimeters below here. So here's 1/2 meter, and then we have a full meter stick up top. So we go ahead and clamp it or click it here, load it, and I'm going to load it with a match. And here we go. So let's see if it goes about a meter high. A little bit higher. It probably went maybe 1.5 meters, maybe 1.6 meters. Of course, a lot of my numbers are pretty approximate, especially the spring constant of the crossbow. That was a little boring, not quite the visual thing I was looking for. Let's try it again. Let me do it again, but this time we're going to put in the match. right? And then we're really going to get serious here. We're going to light it. We're going to light it and shoot it. Let's see what'll happen then. There we go. This demo is lit. Here we go. And, oh, much better. Now I want to show you another way to think about the relationship between forces and energies. So one thing we know is what we've done so far is we calculated these potential energies, gravitational and spring, by calculating the external work. Right? We said that the delta U is the integral of some external work, F dot dr. We really didn't have a fundamental formula for the potential energy. It came directly from this. We put in the force related to the interaction, spring or gravity, and we did the integral. We either got mgh or we got 1/2 kx squared. And this formula makes sense. If you have an external agent doing work, it's going to increase the energy because it brings in energy from the external environment. You could also write it like this then. You could say it's equal to minus the integral if you have an internal force dot dr. So this is a way to just think about the system in and of itself without thinking of an external agent. So let's do it real quick for the spring. So let's say we had a one-dimensional spring sitting here, and this is its natural length at 0. We could push it this way. And what would happen if we push it this way? Then we would have an R that way, and the spring force, the internal spring force pushing on the mass would be that way. Have spring. And if we displace it over here, we would displace it, R would be that way, and the spring would pull it back. Right? The spring force would be that way. So sure enough, this also makes sense. They're the opposite directions. The dot products will come out negative, and that negative, and you'll get that U is positive. The U increases. The potential energy in the spring increases when we pull it this way, and it increases when we push it that way. In fact, you could even make a plot of the spring potential as a function of this axis, right? So if this is x, and this is x, and this is 0, you'd get the 1/2 kx squared. It'd be positive on either side. So you could plot it like that. And that would be the energy. So the potential energy. We can get something else from this, though. We can apply the fundamental theorem of calculus. Mental theorem of, I'll try to write all fancy. That didn't go well. Okay. So if we apply the fundamental theorem of calculus, we know if the difference in this function is the integral of its derivative over a region, then you can flip it around and say that the derivative of the f that we're looking for, we'll do one dimension here, f in the x direction, is minus du dx. Right? In this case, we'll put s's. Right? The minus derivative, spatial derivative of the spring energy is equal to the force of the spring. All we've done is apply the fundamental theorem of calculus, and we kept the negative sign along for the ride. And you can kind of see that this makes sense. All we got to do is say, okay, what if we're right here in this state? What is the slope du dx? It's positive. All right? This says you take that slope positive, make it negative, and that's the direction of the force. So that means the force would be this way. And sure enough, pull the mass out, the force is that way. Well, if you come over here, way back here, or shove the mass all the way to here, du dx is negative, but you stick a negative sign in front, so the force would be positive direction. And sure enough, force is in the positive direction. And it's not just the direction, you actually get the right magnitude. If you were to actually work it out, 1/2 kx squared minus d dx of 1/2 kx squared, right? That's us. What do you get? 2 times 1/2 is 1, kx, you get minus kx. And sure enough, that is the Hooke's law force. But this is the general way to get a force from a conserved potential. And in physics then, if we're going to think about a mass on a spring, we don't actually think about plotting the force. That would be weird. We always plot this. We always think in terms of energies and plot energy. An example could be, what if we wanted to think about a vertically hanging spring? Right, here's a vertical spring where we want to have to deal with, we got to deal with both the spring potential energy and the gravitational potential energy at the same time. Right, that can be done in terms of kinematics, but here's how you could do it in terms of energy. You could say, let's look at the gravitational potential energy. Surely that's not right. Okay, so that would look like this. Let's see, U, G, as you move up and down. So we're going to make up and down this axis because this axis is U, right? And we're doing a spring with a mass on it this way, where this is the y-axis. All right, so we're thinking about the spring moving up and down in y, but we're plotting y this way. Okay, what does the potential energy do? The gravitational potential energy do as you move up and down, it's just linear, right? mgy. So it looks like this, right? If you call this 0, it can go negative if you move below what you would call 0. Right? Let's look at the spring. Yes, spring we just did. It looks like this. If we're talking about y, compressing the spring up and down, and we wanted to plot us, it would look like what we just drew. Like that. Little spring potential. And we can check it. Let's see, if we go to here, we got this, the gravitational force. We could say F is minus du dx. The slope here is negative, right? So let's see, this is going to positive y, right? Right, so the slope the slope here is positive. Right, the slope is positive. Minus du dx is going to give you a force negative, a force down. Yes, the gravitational force is down. Anywhere you go, the slope is positive, therefore the force is down. Makes sense. This works for the spring just like we showed a minute ago. So the question is, what happens when you have a mass here, the spring's at its natural length, and you turn on gravity? It falls a little bit, and it reaches a new equilibrium position where it's the length of the spring plus a kx force equal to the mg force. You got to cancel the spring gravitational force, but you still end up at sort of a minimum. So the way you would get that in physics is you just add these two potentials. Do it on a computer. Just add a negative slope line with a kx squared polynomial, and it's going to look kind of like this. Hopefully I can draw it well. If we do ug plus us, it's going to kind of, I think my artistry will work here. The key is that this was 0, so it's going to kind of do this. Oh my God. Wow, that was really, well, it started out really well, right? And then, yeah, it's going to kind of do that. So this potential really just shifts down and to the left. And the new minimum where it wants to sit, the new place where the force is 0, the force is 0 because du dx is 0, is lower, right? We've gone to further to negative y, where this is plus y. And that's what would happen. If you suddenly turn on gravity, it would go lower. And it would still be a potential well that looks like a spring, and it would still oscillate up and down and everything. So in physics, we often think of them more like this. We think in terms of potential energy. I can give you another example, getting into something somewhat research related. If you have little particles in solution, little nanoparticles or colloids, they're often stabilized through electrostatic forces, right? So if you have a positively charged particle and an identical particle, so its surface chemistry makes it positively charged, that will keep them stable because all particles are attracted, right? So they'll feel a van der Waals force, basically as the force of the little dipole moments fluctuating and the dipoles attract each other. You get a little dipole moment fluctuation in this one, creates an attractive dipole moment in this one. So that's called the van der Waals force. Everything is attractive by this interaction. But then you also have a repelling electrostatic force, like that, because like charges repel. It's actually screened. It's not the one you would calculate in electrostatics, but it's still repulsive even though it's screened by ions. So very complicated system, but how do we study it? In physics, we just think about the potentials, right? So we could plot the two potentials. They both come down very fast. So if this is the separation between the surfaces of the particles here, like that, d, so this is when they're touching. You don't want them to touch. This is when they're far apart. Then the van der Waals looks like this. It comes down really fast like that. And the electrostatic, right, because they want to be far apart, it's hard to bring them together. I'm sorry, this is electrostatic. This is UE, right? They don't want to be close together. They want to be far apart. And the van der Waals wants to bring them close together, so that's that one, like that. But these two things have different scales for their decay. So when you put them together, it looks like this. The energy comes down like that. And you get a minimum here at some separation. So this is U van der Waals plus U electrostatic. You add those two potentials and you say they have an average separation of D naught. Therefore, they don't collide, they don't collapse, they don't aggregate with each other. They all sit about D naught apart. So this is how we usually think about forces and interactions in, physics research world.